review number 7 this week. Okay, on Friday at around 2:04. Okay, at 2 to 3 p.m. this Friday. Okay, we're going to have our makeup lecture next Tuesday between 6 to 7:30. Okay, so you will happen at the Holland Building, room number 106. And the very last one, which is very important to you, if you feel like you are short of points. Okay, so we're going to do the final survey next Tuesday. So this will happen roughly around 15 to 20 minutes before the end of this class. Okay, so what's going to happen is actually I will, just like last time, I will give you a phone. Okay, on the phone, basically have all your names. Okay, once you finish your survey, sign your name on that sheet, and I will give 1 point whoever do the survey. All right. So make sure you will be here next Tuesday. All right. So in our previous lectures, we discussed the ideal solutions. Okay, and we also introduced the concept of partial molar Gibbs free energy, okay, which is mu, and we know the mu of the conformance can be expressed as mu I 0 plus RT natural of xi, and this is basically the chemical potential of less specific substance under a standard condition, which is 1 bar, 298 K. Okay, and if you have a mixture in the solutions, then you need to add in some terms to correct the effect of mixing. Okay, so let's say it's coming from here. It's RT natural of xi. So it's really depending on the more fractions of less specific substance inside the solution. So whenever I write an equation on the board, on the right hand side is the equation to remember. Okay, so based on this, you also derive the equation of Raoult's rule. Basically, you can estimate if you have a mixture of substance inside a solution, then the vapor pressure of less substance can be calculated using this equation. Okay, where the vapor pressure of less substance is equals to the vapor pressure of pure substance times the mole fraction of less substance inside the solution. Okay. And if you want to calculate the total vapor pressure of less solutions, you can use these equations. Okay. So in our examples and also in your exam, we only discuss the binary system, which means inside your solution you only have 2 components. Okay, so let's call it components A and B. Okay, then you can calculate your P total using PA star times XA plus PB star times XB. So it's very straightforward, right? It's just an application of your Raoult's rule if you have an ideal solution. Okay. PA star stands for the vapor pressure of pure A. Okay. If you have pure A as a solution, then that's the vapor pressures you're going to have. Okay. And once you have this, okay, because you are expressing things in terms of mole fractions, so you know XA plus XB is going to be equals to 1, which means your XA can be expressed as 1 minus XB. You can put these things inside here, and you're going to get the final solutions shown up on your handout. Okay, but this is basically the idea. It is where all the things come from. And then we also say, okay, you can also expect, okay, if you have binary systems at a given temperature, okay, let's say at T, K, okay, you can plot out the vapor pressure as a function of chemical composition, okay, which means we use the x-axis we typically use XB. This means the mole fraction of conformant B. Okay, and if you have a pure, if a B XB equals 0, that means at this point you have pure A. Okay, so if you have pure A, you know you're going to have a corresponding vapor pressure of your A. So that's PA star. If XB equals to 1, that means you have pure B. Okay, then you are going to have PB star. Okay? So when you mix A and B together, you can calculate the vapor pressures of your A and B individually, and we follow a linear relationship. Okay? And that's why you have this PA is going to equal to PA star times XA, or PB is going to PB star times XB. Okay, it's linear. Okay, and then you know, if you want to calculate the total pressure of the system, basically it's just the sum of these two curves, because they are all linear, so the summation will be also linear. Okay, so you know this blue curve is actually your P total. Okay, and this is your P, B, and sorry, PA, and this will be your PB. Okay? Alright, so once we discuss, we say, yes, inside your system, let's consider a system look like this, okay? You have a container, okay? You have a piston, outside you have some external pressure, okay, and it's at equilibrium. And this is your solution, contains your A and B, right? And under any given pressures, you know, A and B is going to generate some vapor pressures, and eventually it will actually equivalates with the B external, right? So you know you're going to have the vapor pressure PA and the vapor pressure PB. Okay? So here we plot out these figures based on the XB, right? So XB is the composition inside the solution. Okay, so this is in this solution. Okay? But from this figure you also know, okay, B is more volatile compared to A, right? So when it becomes vapors, there will be more B become vapor than A, right? So if you plot out the chemical composition in the vapor phase, it's not going to look like this. Okay, all the curves we draw so far represent the chemical fractions or chemical compositions inside the solution. Okay, if you can plot out the XB V, okay, which means, sorry, let's call it XIV. Okay, that means the more fractions of one component in the vapor phase. Okay, and that can be described by another curve. So, if you want to know the chemical potential of given pressures, okay, in the vapor phase, then they can describe by this curve, okay. And how do you know the relative fractions of each component? Then we use these equations, okay. So Xi in the vapor phase is equals to Pi star times Xi. This is actually the vapor pressure you're going to generate from the specific components. Okay? Divided by P total, is the total vapor pressure inside the container. Okay? If it's more volatile, you know your numerator will become larger, right? Therefore, the population of less specific component in the vapor phase will increase. Okay, so this is how you calculate the chemical compositions in the vapor phase. Okay, if you do that for every single composition, then you can map out this curve. All right, and if you have And this, at these 2 points, okay, the vapor phase and the liquid phase, they are all pure materials. They actually fall on the same points. Okay? So the same thing applies for your A. But that's pretty much all the things we discussed last time. Alright? So you should be very clear for ideal solution. This is all for ideal solutions. Okay, so make it more clear. This is all for ideal solution. Okay? So today we're going to discuss a little bit more. I will give you examples about this, and we're going to move to the non-ideal solution. Alright? So that's what we're going to do today. Okay.